This is recitation 6, and today we will talk about Ohm's law. We will deal with resistors. What is a resistor? So if I have a piece of wire and I measure voltage across this device, then if it happens that ratio of voltage to current stays constant, then this device is called a resistor. So this is Ohm's law that tells us that ratio of voltage over current for the devices that are called resistors stay constant, and we call R resistance. From experiments, we know that if we have a piece of wire, I will draw it again, this piece of wire will have length L, so this is cylindrical wire, I just enlarge it, length L, cross-sectional area A. Then if I have current through this wire, current I, then the resistance of this wire is resistivity rho, that depends on the material, resistivity, then length of the wire, and divided by the cross-sectional of the wire. I remind you that current by definition is rate of change of charge, and current is in the direction opposite to motion of electrons, to the direction of motion of electrons. So this is current. And now we need to derive another form of Ohm's law. So what I will do, I will rewrite the resistance as ratio of voltage and current. If I write the difference in the electric potential of voltage here, by the way, here we have absolute value. Resistance is positive by definition. So if I write delta V, difference in the electric potential across this resistor, delta V, or in this formula it will be just V. It will be, if electric field is constant, we know that this is integral, I take absolute value from R1 to R2. He is minus, but I take absolute value, E dot dr. So if electric field is constant, then I take it out of this integral, and this delta V is just electric field times length of the wire. So I bring it here. V is EL divided by I. Now let's rewrite it. I have E, which is RI over L, and we will write R as rho, resistivity, L divided by cross-sectional area of the wire. I remind you one more thing. So cross-sectional, this L is in the direction of current flow. So current is flying in this direction, then we care about this length of the wire. So R is rho L over A, then current I, and divide by L. So L and L, and I have rho resistivity current I divided by cross-sectional area of the wire. Now we need to introduce one more definition. We need to introduce current density. We call it J. Current density dot product, this is J, current density, and dot product of J and area vector J dot ds is current. This is definition of current density. Now, if J is constant at each point of this wire, then I can take J out of integral. We will have I is J times S, and we will have J as I, let me do this. I don't want to change the notations. Integral ds is just s, area, and we call area a. So I will write j times a, and then j is I over a. This is a current density. Now I write current as j rho, I is j a divided by a, and I have the electric field as rho times j. Since j is a vector, and the direction of the vector is in the same direction as direction of current, and the electric field is in the same direction, so I can write the relationship between E and J in vector form. They are in the same direction. E is rho J. And this is another form of Ohm's law that we will use a lot when we work with circuits. And we will need both forms of Ohm's law for today's recitation. So one more formula that we need today, this one, V at R2 minus V at R1, and this is equal to minus integral E dot dr from R1 to R2. So this is not a problem, this is the review of all formulas that we will need today.